It's my pleasure to introduce Robert Graham, who was the first to write a highly performant IDS for Windows.
Well, for everything.
For x86.
For everything. Ran fine in Spark and ARM as well.
Yes. So if you're interested in, throughout this class, we talked about the kernel and how the kernel protects the data and how the kernel is stacked, as in for the protocols that wrap other protocols, as in, say, for example, TCP/IP packets, how the kernel's structure reflects that encapsulation. Robert is going to show us that this is not exactly an optimal architecture for high-performance packet analysis, and in fact, the kernel might be the problem, not the solution. Sorry, what's an IDS?
Oh, intrusion detection system.
Okay.
Monitors network wire looking for bad stuff. Yeah, so my talk at ShmooCon's a hacking conference a couple weeks ago. I focused on this idea of scalability and how the kernel doesn't do scalable. So you have your professors like Sergey here, who teaches you all the wonders of Unix. And so I'm going to teach you about how everything about Unix sucks. And it's not that it's a bad system, it's bad for high performance networking. So for a lot of things, it's great. It's what it's designed for. But high performance, really, really high performance stuff, or scalable stuff, is not what it was designed for. That was sort of a fringe thing. And it shouldn't be, because you make trade-offs, and trade-offs for scalability are different than what Unix was designed for. So the start of my talk, I want to talk about scalability. And this is a graph of what performance looks like for, let's say, an Apache web server. For a small number of concurrent TCP connections, performance is pretty much what you would expect. But as the number of connections increase to the server, the performance starts dropping pretty rapidly. So Apache is well known for, if you try to open up 10,000 connections to it, the performance just crawls to nothing. And so let's say that you want to, well, I've got one that performs adequately at, let's say, 5,000 connections. And I want to increase the speed or increase the scalability so that it'll handle 10,000 connections. So what do? Do I just buy a server that's twice as fast? Well, that's what this graph shows, is that server, but now twice as fast. And as we see, indeed, it's now 200% as fast for a small number of connections, but for 10,000 connections, I haven't got any closer to that goal.
So what's the bottleneck?
The bottleneck is your basic big O problem, that it's n-squared performance, that in terms of number of connections. And that's why the performance, as you increase the speed, you're going only a little bit up the graph. So if I quadruple or 8 times the speed or 16 times the speed, I'm still not reaching my goal. And that's what you expect. That all this graph is, it's not actually a benchmark. All I did was graph n-squared. So that's all this graph is. So the point I was trying to make is how we still don't reach the 10,000 connections. An alternative is to choose, of course, as we know from our complexity class, is that we'll choose a different algorithm of something that looks different. And that's what a lot of modern servers do. Like Nginx is the hot new server to replace Apache. There's also other toolkits like Node.js for building web servers that has its own built-in web server, but you program everything in JavaScript. Do you guys know Node.js? So Chrome came out with their own JavaScript implementation called V8, and they made V8 a separable component that would run the command line. So some other guys said, well, we can make a server out of this, and that's what they did. And it scales is the thing about Node.js, and that's what this orange line is supposed to show. Is Node.js is just JavaScript. So it's slower than Apache. But since it scales, at 10,000 connections, it's a lot faster than Apache. And that's the point I want to try to make about scalability, is that performance and scalability are sort of these orthogonal concepts. That things you do to increase performance is a different set of things than the things you do to increase scale. And that's what my talk is really about, is what do I need to do to achieve scalability? How do I get to 10,000 connections? So this talk was for the ShmooCon crowd, only a small number which are coders. But everyone else is sort of a manager or a hacker or something else. I guess you guys are more interested in the code. So the previous decade was defined by this concept called C10K. How do we make servers achieve 10,000 connections? This talk was to go to really the next level of 10 million connections, and the scalability, the new scalability concerns that we have to tackle that. And the biggest issue is the kernel and how to bypass the kernel. And then I focus on packet scalability, multi-core scalability, memory scalability. Each of these three areas has a special concern of what we need to do different to achieve scalability. So let's go back to the order of n squared issue. So in the past, with connections, the way that Apache works is that it assigned a thread for every TCP connection. So you have an incoming connection, you accept it, then you handle it, you spawn a new thread or pull from a thread pool and handle it. It's not exactly order of n squared. The real thing is it's number of packets times number of threads. And as network goes up, both increase. The number of connections increase, the number of packets per second increase. And most people describe this as a linear thing, order of n, because thread scheduling required walking the entire list of threads. So that if you wanted to go from one thread to the next in the kernel, it would walk all threads. And they describe it as an order of n problem. It's a linear problem. And it really wasn't, because it's every packet that comes into the server causes a thread context switch. Every packet that comes in refers to a random TCP connection, which means a random thread. So the correct way of thinking about it was an order of n squared, or n times m, where n is the number of packets and m is the number of threads. So you have an alternative way of constructing a server is using select or poll, but that has sort of the same order of n squared problem. That in this case it was walking the entire poll list for every packet that came in, and the more connections you had, the longer that list of sockets. So back 10 years ago, they fixed the kernel. So you look at what a lot of Linux changes back then, or Solaris, or other operating systems. They added functions like epoll. Epoll is the Linux thing that works a lot like poll, but yet the transition for sockets is constant instead of linear, which means as packets come in, you scale with the number of the traffic level. And then the solution we look at for Nginx and other things is to move to an asynchronous architecture. And what that means is instead of a thread saying, read from network, then read from disk, and then send the disk information on the network, it was asynchronous. It's like when a network packet comes in, do some stuff. When data arrives from the disk, do stuff. And you just have a little central dispatch loop. And so if you want to write a scalable server yourself to go to 10,000 connections, you'd use a toolkit like libevent. Libevent is a great little tool for doing this sort of coding. And it runs on top of whatever the underlying scalable polling mechanism is going to be, like epoll for Linux, or I/O completion ports for Windows, or other stuff. And if you want to install a scalable to 10,000 connection server, you might want to play with Nginx, that's NGINX, or Light HTTPD. And these scale pretty well to 10,000 up to about 100,000 connections. And the importance of the scalability issue is shown by this graph, where Apache has dominated the world for many years, and now we're quickly seeing that Apache is being replaced by Nginx. So this little green line is Nginx, and Apache is going down.
What happened last May?
What happened last May?
Yeah, there's a very specific chunk of Apache sites switched to Nginx.
Yeah, there's the little ding there.
I don't know. It's in that graph. So also, this is the million busiest sites. So when you look at all sites, Apache is even more dominant. But for busy sites, they're really hitting scalability limits. They have to replace Apache and go something else. So all your professors, if they teach you solutions with Apache, they really should be teaching at least Nginx as the starting point.
Nginx is unreadable. This is what they call. This is what I hear from reverse engineers. This is what they call the Russian electric engineer style. No variable name is longer than 3 characters.
Of course not. That'd be just inefficient.
Yeah,
If you reduce variable names from 6 characters to 3 characters, it'll run twice as fast. Everyone knows that.
Well, that's in Nginx.
So, but my talk isn't about Nginx. It's about after that. So the problem with Nginx is still that you're going through the TCP/IP stack in the kernel, and that goes to about 100,000 connections. So what I'm talking about is going to 10 million connections. Or there's other scalability limits that you might think of other than just concurrent connections. So one of which is 1 million connections per second being established and destroyed per second, or requests per second if it's HTTP, about 10 gigabits per second, 10 million packets per second. Also there's latency, 10 microsecond latency. Whether I'm a server or a router or something, I need to take a packet in and get the response out very fast. There's also max latency. This is one of the big things where the kernel breaks down, is if you're writing a kernel and your normal thread, it can be scheduled out at any point in time. That means that the packet that you received is going to take you maybe several milliseconds to respond to. So your maximum latency just goes out the window trying to get to do things the Unix way.
And we have seen that in the Solaris kernel, in the preemptibility of the Solaris kernel. With Linux kernel, with the old style of synchronization primitives, you just can't guarantee a real-time response. Solaris took a fair amount of engineering to have a real-time scheduling class.
Now,
threads.
by the way, you're not really looking for necessarily real-time, though you might use the real-time primitives. Real-time is a concept you'll use for a lot of control systems, like you're controlling a mechanical device that's punching parts out for a car, and you want things to happen at a certain time. And for networking, your requirements are not necessarily real-time. It's just that if I've got a VoIP server and I'm doing internet telephony, I just can't hold on to a packet for too long before it's going to become noticeable. And it's not just my latency is the issue, it's everyone's latency in between. So occasionally it's not so bad that you actually, if it's 1 out of 1 million packets that takes a millisecond, yeah, you can deal with that. It's not such a big problem. It's just that where it would be for an industrial control system. So real time versus what I'm talking about here, they're kind of related, but they're not necessarily related.
So you say something about the 10 coherent cores?
Oh, yeah. So the other issue is to reach high levels of scalability, your code has to be multi-core. So right now, the way your professors are teaching you to write multi-threaded programming fails to scale to 10 cores. And so I'm going to discuss that in one of the sections here. By the way, I'm blaming Sergey for everything.
Oh, okay. I am definitely a Unix, well, not necessarily a Unix zealot, but a Unix believer.
So what sorts of things need this sort of scale? And it's things that serve the web. They're exposed directly to the web. And it could be things ranging from like a DNS server to a Tor exit node. You guys all know what Tor is, right? I assume you all do. A video streaming server, a high-end banking app. These are all things that sort of need to have this level of scalability. It's not just a few thousand people you're serving, it's the entire internet with billions of people. So my talk is for people like us that write software on top of a standard x86 server. But there are devices that do this already in other ways. And those are appliances or devices you plug into the network. And these are sort of positioned as hardware, as if they're doing everything with a custom ASIC or a FPGA or something. And that all the magic somehow done with hardware. In reality, these devices are generally just your RISC processors running software. And if you pull open the boxes, indeed, sometimes you'll find just x86 processors. So back a few years ago, I worked for a company, and our competitor said, "Hey, we're better than my product." The competitor said that their product was better because it was based upon hardware. But when you pulled open their box, everything was just being done with the standard x86 server. And they had an FPGA that would do some preliminary network classification, but when you reverse engineered their code, It was all the heavy lifting was done with x86 software. They had no real special sauce in hardware. And that's so all the devices you go to your computer center and right now to the racks of the devices like routers and servers and routers and I don't know other devices. A lot of them are just software, and they're software that you can write on x86. So the sort of system you would need to reach the scalability is about $1,000. So my code does this level of scalability on a $1,000 computer using 8 cores with 32 gigs of RAM. If you can't, and it's really highly tuned. If you can't really highly tune it that much, you probably can't for most applications. You're going to spend more like around $5,000 for a server. And so a server for $5,000 can easily scale to these levels. So you guys all used this textbook, I assume? Stephen's network program. This is actually a picture of his older, previous version.
Yeah, I quite like this textbook.
I know you do, because you're wrong.
It's the best introduction to programming Unix for some reason. Far apart from network programming, it really tells you about the programming environment. But yeah.
So the reason I popped this up is because it really is a Unix book and not a network book. So a lot of people in our community of hackers and cybersecurity people, we learned networking from this book. But this book really is, as Sergey says, it's about Unix more than it is about networking. It's really a horrible introduction to networking. But nonetheless, this is how how they learn networking in college. Do you guys have
EZPIP Illustrated?
Yeah.
That's the one to go for.
Yeah, that's what I go for.
But still, that's wrong. And so it taught you guys a lot of bad habits. One of which is this issue of endianness or byte order. We all remember, I assume you guys all remember that, this epiphany you had, like, wow, byte order, it's something I hadn't thought about before, and now it's something new and interesting. And what Stephen's taught you about byte order is wrong. So there's 3 correct ways of representing an IP address. There's the string form, there's an array of bytes, so we know it's big endian, so it's going to have the high byte first, so it's 10, 1, 2, 3. Or as an integer, and the integer that's represented as the hex integer. And these are the 3 correct ways. What Stephen's teaches you, and it's really not Stephen's, it's the whole sockets infrastructure back from BBN when they put TCP/IP and BSD Unix, where they teach you to cast the integer, and then to byte swap the values. And this is the wrong way. This is something you should never do. And that it is wrong is proven by the fact that you can't do it this way, like in Java or JavaScript or Python or any other language other than C. You can't cast the bytes, and it's the casting of the bytes that cause a problem. So people who learn TCP/IP Illustrated or networking from a C perspective, later in life they're constantly confused with byte order and making byte order mistakes and swapping things wrong or swapping things twice or making lots of mistakes because they really haven't paid much attention to it. They sort of know it, they can define it for a test, but they really ignore the issue, and then they make mistakes. But programmers that started network programming from a Java point of view or a high-level language, they never get confused because things always look like this and they're always correct.
Can you say why it is wrong? I mean, a cast. Why cast is wrong?
Because it's undefined. C doesn't define what it means. So on a Spark processor or an x86, you get the opposite result from the opposite byte order. Also on a Spark processor, it'll crash if it's not aligned correctly. And so it's wrong from the point of view of theoretical point of view. From a high-level theory point of view,
Philosophically offensive.
It's philosophically offensive. We know it works. We know what's happening really underneath, but philosophically it's wrong. And it's not just this. It's the whole idea of taking an internal structure of a struct and then casting it to a pointer to a packet. I'm going to dereference all the individual fields of an IP header.
Well, you can think of it this way. This integer, this multi-byte integer, is sitting could be sitting in a packet, and you could be looking at it through the pointer to the buffer. Now, in order to interpret this as an integer, though, think of a port number. Port number is good. Port number is 2 bytes. Right? It's a 16-bit number. So before you can actually treat that integer that came to you over the network as an integer in your code, you have to convert it to host order. So integers that come to you in packets cannot be used straight up, straight, in the packet as they arrived. You have to surround that with a conversion function. And so you have network to host short, network to host long, and so on.
So the philosophical viewpoint, the correct one, is that there's external data that's in a file format or in a packet, and it's external. It follows rules that apply only to the external world. And that I've got internal data structures, and they're internal, and they follow rules to the internal world. And you should never mix the two. You should explicitly convert one to the other, never this implicit conversions like, I know what's really going on here and it works. It's still philosophically wrong because you've made that assumption. And from a hacking point of view, that's a big thing, and why hackers can do what they do is because people are ignoring this translation step, and they're implicitly trusting what's in the external world, which hackers can manipulate. RPC is what was like the worst thing like that. They would take an internal data structure, marshal it, send it across the network, and then unmarshal it and have another internal data structure. And both sides would treat it as an internal data structure, and ignoring the fact that at some point it was external, and hackers could have manipulated it. Which is why 10 years ago you had all these RPC worms that were either Sun RPC or Microsoft RPC that were just devastating the internet. So here's a little bit of code. You print off of the D reference, and you see that yes, on x86 the bytes are reversed. Or in a Spark, this program would crash if it were unaligned. So the message I was trying to get here was that the kernel isn't the solution to your problems. The kernel is often the problem getting in your way. And a lot of what Stevens taught you gets in the way. So to start with, let's talk about asynchronous programming. So Apache works, it calls the read function, and if there's no data on the socket, it blocks and stops, and the thread stops. Then the thread scheduler goes into the kernel. The thread scheduler then finds another thread that had called read in the past that's got now data arriving from the network. And the thing about that architecture for Apache is that your thread scheduler is now your packet scheduler. And that's the problem, is that it's a very, very, very inefficient packet scheduler. And using select or the more scalable epoll, you do the scheduling yourself. You worry about when a packet arrives, a socket arrives, well, what code do I need to call to process that socket? And the idea from a low level is what you're doing is instead of letting the kernel do all your scheduling for you, you're doing the scheduling yourself a little bit more yourself. So Apache threads blocking Nginx, single-threaded, non-blocking. So Nginx does this with a single thread or one thread per core, and it worries about all the scheduling stuff itself. So now I'm going to talk about packet scheduling. This is where I start to get into the meat of the presentation. Is we have, this is the Linux kernel map. I got this from Wikipedia. I don't know if you've seen this before. And the part that I want to talk about is the networking stack. Specifically, when a packet arrives, it takes this going to the network device drivers and blah, 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 all through all these structures and stuff, all the way up the stack. And it's a very convoluted path. It takes about 20,000 clock cycles from when a UDP packet arrives here for it to appear when you do a receive from in your code.
And we've walked that path, if you remember, on the Linux kernel through the net filter structures.
Now, when you've walked it, you've walked through a fairly idealized version because you haven't done it at scale, like at 100,000 connections, when a lot of these structures it starts dereferencing are all cache misses. So when everything's in the cache, you get one set of timing for this. When everything's not in the cache, you get 100,000 connections. A lot of these structures, like the socket structure, the TCBs, none of that's in the cache for that connection. And so now you start hitting cache miss after cache miss, which balloons that out.
Yeah, correct. So we only looked at these switches on the protocol numbers embedded in the packet.
So one thing to look at is to look at, well, how do when I hash the socket information, the IP port numbers, how do I do that hash lookup to go into to look up that TCP connection? So my approach, wait, I did this 10 years ago. It's now actually not my approach anymore. A lot of people do it. Is to just take the packet itself and just send it directly to your user mode application. And what that means is you write your own custom driver for the hardware. And I say you write your own, but things now exist. For FreeBSD, you've got NetMap, and for Linux, you've got pfring. And what these drivers do is they write their own driver. They memory map a buffer up here in user mode and give it to the kernel, or vice versa, and use that as the incoming packet buffers for the network driver itself. And what that means is the network driver is configured to DMA the packets directly into that buffer. And so what that means is with the CPU doing no effort whatsoever, executing zero clock, executing zero instructions, packets have arrived in memory, in user mode memory, because it's been memory mapped for the application to get at it. So that's zero overhead. There is a little overhead eventually, because eventually that buffer will fill up. You need to free the buffers and tell the card, hey, these buffers are free. But on average, that's about 50 instructions per packet. So we've gone from...
Is that any different from just user mode drivers?
It's effectively user mode driver. I look at something like pfring. The drivers that I wrote 10 years ago were completely user mode. So from the user mode, we would memory map the control structures across the PCI bus, and we would just write to them to free the packets. So we did all this stuff in user mode. Besides the kernel work to set things up, from that point on, it was all user mode. pfring, I think, does a kernel thread to free the packet buffers. I don't know about NetMap, or there's a lot of commercial drivers too.
There is IPQ or NFQ, which is a part of the Linux kernel, which allows you to steal packets out of the kernel. But
Right.
I don't believe, I believe that copying is involved there. So
Right,
the
I
packet would be copied across from outside of the kernel to your userland, to a queue where your userland application
Right.
would take it.
So the upside is you go from 20,000 cycles to 50 cycles. It's going from a huge amount to effectively zero, as far as your application is concerned. So for you guys, you can play with like pfring, NetMap on FreeBSD. Both of these are they're okay. Intel has, for commercial people that write, or if you're a commercial people, you might want to license Intel's DPDK. It's called Data Plane Development Kit. There's more third-party support for Intel stuff, so you can buy your own user mode TCP/IP stack on Linux called 6Wingate, which actually works pretty well, which a lot of these network appliances are using inside, like on a MIPS processor, on a 8-core MIPS processor or something. But these would be the things that you play with. Intel has benchmarked their DPDK in just forwarding mode, of forwarding packets, taking every packet coming in on one side and just copying it out to the other side. And on an 8-core CPU at 2 gigahertz CPU core, one socket, they're doing 80 million packets per second, which comes out to about 200 clock cycles per packet. Now, when they use the native Linux stack in bridge mode, Linux can do about 12 million packets per second. But that's with all the packets staying at a fairly low level in the kernel, going from one device driver to the next device driver, not even getting to the point of net filter, or much less up to the user mode. Intel did this in user space, so it was DMA'd into user space and DMA'd out. Now, 200 clock cycles per packet is less than a single cache miss per packet. So in the old days, these packets would be DMA'd into RAM. But that would mean that, of course, would invalidate the cache lines, which means reading it back out again would then be a cache miss, and be probably 300 clock cycles per packet. And the reason it's less than one cache miss is that these days, Intel hardware DMAs the packet into the cache. It doesn't even hit memory. So you can get a packet coming in and back out of the system again without it ever hitting memory, on average, on a per packet basis.
That's remarkable, because recall all of our considerations of cache coherence. Now you have a channel into that cache from the network card.
Right.
So what sort of games does that play with your cache coherence?
And presumably there are x86 extensions that let you fiddle with this. Can I do this?
Yeah.
Do you know what they're called?
No.
The family.
It's a new feature. It started in Sandy Bridge, and it comes from the fact that in the Halo and on up, you now have an integrated memory controller, and the L3 cache, it's really the last level cache, is really a very separate system that's between the memory controller and the rest of the components, the rest of the cores or the GPUs that are now in the chips. So the L3 cache now is what runs everything basically off of the L3 cache.
Right, because all of the cores share the L3.
For all the cores,
Whereas they each have their
the
own
GPU
L3.
shares the L3 too.
The QPI link to other sockets goes through the L3 cache. So everything is L3 cache. So unlike multi-core programming, when you're doing atomic instructions, it's atomic down to the cache and back again to the L3 cache. So it doesn't even, so older Core 2 processors or Pentium 4s, they would sit on a memory bus, and so an atomic swap or something had to go out to memory, so it would take 300 clock cycles. And now it just goes to the L3 cache, which is 30 clock cycles. So the L3 cache everything is run through the L3 cache, including now the packets. So if you get packets coming in and out and they don't invalidate, doesn't need to reuse the cache lines, it just never goes to memory. So if you're running PF_RING, you're getting the raw packets. So you don't have a TCP/IP stack. So you need to either write your own, or if you're running something like an IDS or a DNS server that's just running over UDP, you don't really need your own TCP/IP stack. You just deal with the packets yourself. But if you got a web server, you sort of need to get a TCP/IP stack. Now there's a number of universities researchers have published user mode TCP/IP stacks that would work off of PF_RING. But there tend to be prototypes rather than something that's really robust.
Is there something fundamentally different about IDS for a web server and just a web server?
The thing about IDS is that you're tracking the connection rather than interacting with it. So there's a lot of things like timers and stuff that you don't need to actually worry about. You never need to have a timeout and then send another acknowledgement or something like that. So, and it's really the timers. And timers get to be a fairly complicated data structure by themselves. That trying to track all the timers and do it in a cache-efficient manner and with limited resources, because sometimes hackers can exploit things to cause your timer structures to balloon out and stuff like that. So just the timers is by itself a hard problem. And with IDS, you can largely discard that.
Generally, with IDS, you can do away with, you can get away with a much less complex model of the protocol.
But at the same time, you've got some additional complexity you wouldn't otherwise have, because you can't interact, and so therefore you can't. Sometimes it's like you're not quite sure what the correct interpretation of a field is. It could be A or it could be B. So you got to sort of then bifurcate your code and say, well, I'll try to do both logic at the same time, and it gets to be hairy and nasty.
Mm-hmm. Well, this is what all the IDS bypasses.
So back in the old days, and this is the really, really old days before even I was born, you had switches were via electrical wires. When you made a phone call, it's because someone in the local switchboard would take a wire and connect your copper wire to someone else's copper wire. And what the copper wires are the data plane. They carry the data. And then the switchboard operators, they were the control plane. They would control how data flowed. When we transitioned from analog telephony to digital telephony, that model carried forward, where you had the whole T1 protocols were streams of bits that were done in hardware, and then computers, the original Unix computers, were control systems for the telephone switches. The Unix systems didn't carry the telephone traffic themselves. They would just configure the hardware to tell the hardware how to route the telephone connections. And that's still really how Unix today is designed. Unix is not designed really fundamentally to carry large amounts of data. We use it to carry large amounts of data because we write our web servers and stuff that way, but it's really not designed that way. And that's why Intel calls their development kit the data plane development kit. It's a kit for bypassing Unix and in a way that actually will carry data much, much faster at much higher rates. So the next thing I'm going to talk about is multi-core scaling. And the concept I want to stress is that multi-core is not the same thing as multi-threaded. A lot of people, we use these things interchangeably because if you want multiple cores, you have to have multiple threads. But the thing about multi-thread programming is the way that we do it today does not scale to a lot of cores. So we see that in software. We take an arbitrary software package that is multi-core, multi-threaded, and we try to run it across multiple cores. And it gets faster for the first few cores. But after about a certain point, and it's usually around between 3 and 5 cores, adding more cores causes it to slow down. And what we want is something different, something that looks like this graph, which is as we add more cores, it keeps getting faster and faster and faster. And even then, we might have imperfect scaling. So if you notice here, at 16 cores, I don't reach 16 times as fast. And I'm only adding cores only adds about 25% of what the value was back at the start. So there's still a scalability problem here. It's just scaling a lot better than the previous graph. So the problem we have with why multi-threading is not multi-core is that multi-threading concepts were developed back in the 1990s when we had only one CPU per system. And our struggle was how to take multiple tasks and to run them on that same CPU. These days we have one task that we're trying to say, I want to split across multiple CPUs. And fundamentally these are different problems. So today the way that we do synchronization is with spin locks, mutexes, a bunch of other stuff, and they all share the technique of stopping a current thread when there's a necessity for synchronization. And that's okay because there's always another thread ready to run on the CPU. But for multi-core scaling, we can never stop a thread, especially if we're doing network applications, got a small jitter budget, we can't stop. So the concept is you think of a spin lock or a mutex or critical section or semaphore as like an intersection where when they collide, some traffic stops, other traffic is allowed to go. But what we want is a synchronization that runs more like a freeway, of where traffic continues to flow in both directions and no one ever stops. So how do we do that? So one way is to think back about the problem that there's ways of doing things that don't necessarily require that robust synchronization. Take, for example, a Linux kernel that tracks the number of transmitted and received packets. The Linux kernel is multi-core, so it's running on multiple threads. Any one core can receive the packet. And you look at the interrupts and you see that, hey, yeah, they're coming in across all the cores. So how does it keep a counter? Is there one master counter for that interface, like transmit packets, that's updated by each core? And if you did that and synchronized it, it'd be really, really slow. So what they do instead is they have one counter for every core. So every core has its own local data that it will update with the transmit count, the receive count. And then when you call ifconfig to then track those numbers, that thread then goes to all the different data structures and just sums them all up. And it doesn't need to do any synchronization. And that's because reads or writes across the memory bus are always atomic. I can either read or I can write atomically. It's just I can't do both at the same time. So each individual core updates these counters itself. It can update with no synchronization problem. And then the reader can then read them all together and have no synchronization problem. So you're going full speed, no synchronization, and it's never corrupted. Where it is corrupted is if you tried to then say, let's look at average packet size, where I take the number of packets divided by the number of bytes, like received bytes divided by received packets. Well, these numbers can actually be slightly out of sync now because we're not doing any synchronization. So there is a synchronization problem. But if you look at your requirements are, do I really need to care about that the average packet size is absolutely positively correct all the time, or can be off by one packet? And that's where you can make these decisions. I don't really need to necessarily synchronize like I'm supposed to. There are also data structures like ring buffers. Like a single reader, single writer ring buffer does not need any special synchronization. You can do that without corruption. There's also a technique of read, copy, update that needs very little synchronization that allows threads to move at full speed forward without having to stop and wait. So for x86, it's got instructions called atomics. You can take the lock prefix in front of an x86 instruction and it'll be atomic. What that means is that the processor will lock the bus. In this case now, it means locking the L3 cache and prevent anything else from hitting that memory. And you can access these in C code with primitives. This is from GNU-C. If you've got So an Intel processor, it all happens in the L3 cache. And what we can build from those is things called lock-free data structures. Do you guys ever cover lock-free stuff?
To an extent, we looked at VMem allocator for Solaris, where the first layer, the so-called magazines, are CPU local.
So some universities have been focused a lot on this, and they've created things like hash tables and queues and lists and other stuff that are all lock-free. So there's this company called Azure Systems. They sell these 1,000 CPU systems. They're all coherently in one memory range. They have a hash table that you can even resize the hash table, and no thread ever has to stop and wait for any other thread. So when there's a synchronization issue, instead of one stopping and waiting, they sort of go in different directions.
And the trick is really that when a thread is scheduled on a CPU, it accesses a data structure bound to that CPU. So
well, no, one thing. Lock-free data structures, no, they're accessing all the same CPUs, the same structures. And so they've developed algorithms, very theoretical ones that work well in practice, of how do we have this dance together, multiple cores, that when we are conflicting, we still don't corrupt memory. And they're really, really creative, and you should read into them. What that means is that I have to restructure my code. I can't simply take a mutex and replace it with a lock-free. It doesn't work that way. I have to think about the problem a little bit at a higher level. But I can change how my code works and get this lock-free structure where all threads can now move forward without ever having a thread that stops.
I have a question. So you want to do atomic operation, right? And you still need to lock the memory.
Right. That's one of the funny things. Is that, first of all, it's called the lock prefix here. So you're building your lock-free data structures by using the lock prefix in x86. And in reality, you are stopping and waiting, because when you're stopping and waiting for 30 clock cycles for the L3 bus. It's just that your thread from an operating system point of view is not stopping and waiting.
And this is exactly the same lock prefix that you see on atomic operations that underlie a spin lock.
Right.
Only it's for one instruction.
And in reality, when you take a look at and deconstruct what a spin lock is and what a lock-free data structure is, they're not as far apart as really the theory says they are. Because a lock-free data structure, instead of spinning and waiting for something, it says, well, I'll try this. It doesn't work, so I'll try this instead. That didn't work, I'll go back to the first thing and try it again. So the code's actually spinning in a fashion. It's just not, conceptually, it's not waiting.
Prasad teaches a class on concurrent algorithms that covers this stuff.
Yeah.
The theoretical side of the stuff.
And performance-wise, it's not actually a win. Sometimes it's actually better to do a spin lock. But you sort of want to start from the lock-free first and then say, well, maybe a spin lock is better, rather than the other way around.
Well, I believe Solaris has a system where it starts on a spin lock, and if it doesn't free up within...
Well, yeah, there's several kinds of spin locks now where people look at a lot of the problems with spin locks. So there's like 3 or 4 different ways that Solaris will do spin locks.
This is the adaptive lock, which should be coming out of people's ears by now in this class. The trick is to take the spin lock if if whoever is holding the lock is running on a different CPU, and to queue otherwise, under the assumption that if the lock has been taken, that it will be freed very quickly. It's that locks are not held for long, and if another thread is active, then it will release it soon enough, and so we can afford what we'll lose for a context switch will be less than what we lose for in cycles for the spin lock.
Right, because otherwise you could get the context switch eventually anyway, but you just could burn the CPU. So these lock-free algorithms are actually very, very difficult to write correctly. There's a lot of problems with writing them. You have to sort of take into account. So you can't really use them willy-nilly unless you've really, really studied the problem. So here are just some things. I'll give you a copy of the presentation. I sort of put a bunch of buzzwords here to Google later. But these are things you have to worry about if you're doing lock-free stuff. So it's not just synchronization. We also have how we want to solve the problem. We have a problem, we want to reduce it to many cores. How do we do that? Well, one way is where each core does a different task. Like take an TCP/IP stack. You might have one core receive the packet, another core processes the TCP/IP headers, another core does the application layer. So that's called pipelining, where each core might have a different task. The other model is the worker threads, where each thread does the same thing. So for example, for a server, it might be that each thread receives a packet, does the TCP/IP header, does the application layer, does everything else, does the response, all the way through from one end to the other. And there's different reasons why you might want to choose each of these things. For example, if there's a part of the system where there's a lot of contention, you really want to say, well, I'm just going to assign one core to do that part of the system. But if there's not, then you want to have worker threads. So for example, receiving the packets, well, they're all feeding from the same packet queue. So there's a lot of contention there. So if you're doing worker threads, they're going to keep blocking on each other or spinning, even doing lock-free algorithms. There's a lot of waiting going on. So what you might do instead is use a pipeline model where one thread receives packets from an adapter and then dispatches those packets to individual worker threads that then continue from that point on and process the TCP/IP stack where there's a lot less contention. So that's why you want to have different models or a combination of one or the other. So how do I do this in a network application? So the way I do it is I take Mac CPUs, or there's another one I should have put here called ISIL CPU on Linux, that tells Linux the kernel only gets a certain number of CPUs, and the rest of the CPUs belong to you, essentially. Linux knows about them, but it doesn't ever schedule any thread to run on those CPUs. And then you schedule your own thread using just the pthread function call to schedule your thread to be on a CPU. And you can tell it, okay, I've got 5 threads, reserve 5 CPUs for me at boot time, and only I get those 5 CPUs. And I assign 1 thread per CPU. Also, twiddle with the interrupts so that those CPUs never get interrupted. So the APIC on x86 systems are the ones that forward interrupts on through. So you only forward those interrupts to the first 2 CPUs, and you use the rest for your own application. And what that means is that you can now create a system where my threads, I can create my own system where my threads never get interrupted. They don't get interrupted for interrupts. They don't get interrupted for scheduling. And I can now guarantee things like a low jitter that my thread will never get interrupted and have something else scheduled in its place. So the third thing, so I was discussing 3 things. It was packets, threads, and now memory. And at scale, the important point is that every pointer that you access is a cache miss.
So this is important. We've seen in, say, hash tables, quite a lot of references to collision lists, right? You have the array that your hashing goes through, that your hash is the index to, and then, of course, you need to follow some next pointer. And you've seen that code throughout the kernel.
Right, and at scale, every pointer you follow now becomes a cache miss. So think back to my original Apache example, where Apache has 10,000 connections, and all the memory associated with it, with the TCP/IP stack, with the HTTP layer, with packets being cached to be retransmitted, it's about 2 kilobytes per connection. If I've only got 10,000 connections, 2 kilobytes per connection, that mostly fits within the L3 cache. Today's server processors have about 20 megabytes of L3 cache. So 10,000 connections times 2 kilobytes per connection is 20 megabytes. And so most of the time, when you follow through a hash table, everything's is in the cache. But when you're at 10 million connections with 2 kilobytes per connection, it's 20 gigabytes of memory. And your CPU still only has 20 megabytes of cache. What that means is when a packet arrives, everything associated with that packet will not be in the cache. So the TCP stuff won't be there, the HTTP stuff won't be there, anything else associated with it will not be there. And what that means is every time it tries to access things, I try to visualize what that looks like if everything is really, really far away from you. All that memory is really, really far away. And when you do a budgeting calculation, so back on that that Intel benchmark where they're doing 80 million packets per second, they're consuming 200 clock cycles per packet. Now, if you reduce that down to 10 million packets per second, which is what my talk is kind of about, that leaves 1,400 clock cycles per packet. A cache miss is 300 clock cycles. So that means per packet, I've got a budget of 4 cache misses per packet. And simply walking through the TCP/IP stack in memory exceeds that budget, because every every pointer it follows is a cache miss.
Including the protocol implementation functions that get dispatched based on the protocol number.
Well, some things will be in cache. So that switch statement probably will still be in cache. But any data structures you've malloc. So the problem is that we're using a lot of languages, especially if you're not doing C, you're doing C++ or Java or something else, where there's a lot of memory allocations going on underneath that you're not really quite aware of. And every one of those memory allocations is a cache miss when the packet arrives. So as you go through your data structures, every time there was a malloc, there's a cache miss.
When the virtual function tables and all that bullshit.
The V tables in C++ just kills you, because it adds an extra cache miss for everything. So, and so you instead of thinking about your memory as just sort of just letting it happen, you got to start thinking about it. Like, well, maybe if instead of doing lots of small mallocs, I'll do like an arena allocator, where I allocate one large chunk for my TCP connection, and do lots of small allocs out of that. And then everything's on the same. Well, it's going to be more on the cache line, but memory happens in bursts. So I burst from DRAM. So it's going to burst 2K from DRAM very quickly instead of accessing things randomly.
Well, of course, in both in Solaris and Linux, you now have slab allocation, when your connection structures or whatever kind of uniform structure that you're allocating.
But that can be a bad thing, because I've got 5 different things I need to allocate from 5 different slab allocators. There's still 5 cache misses. Where if I allocate one large chunk from a slab allocator maybe, but then subdivide it myself, I get better performance.
Can you reserve physical memory on Linux exclusively, like you can reserve processors?
Yeah, you can, but you don't really want to. What you want to do instead is huge pages. So that's what this is about. So your page size now on Linux or on x86 is 4 kilobytes in size. So the page tables, if I'm using 32 gigabytes for an application, that's what all the 10 million connections or needs 32 gigs. That means I'm going to have 64 megabytes of page tables. That doesn't fit in the cache either. What that means is when a packet comes in and I reference it memory based on that packet, that will be a cache miss. But the page table entry I need to resolve it to convert from virtual to a physical address, that's also a page miss. If I'm in a VM, that's another level. It's another paging level abstraction. So that's 3 page misses, three cache misses for every memory access. The solution to this is huge pages. Paging is done in a hierarchy. It goes from multi-terabyte pages to a half terabyte page to a 2 gig page, to a 1 gig page, to a 2 meg page, to a 4K page. So you can go up that table and choose a larger page size.
In fact, in the page table entry and page directory entry, there is a bit that you can set. It's called the large page bit, which gives you 2 megabyte page.
Right. So, and that's really cool. So now what you do instead of reserving physical memory, you just tell you reserve huge pages. And you want to. Well, I'll get to that. You actually want to, like on boot time on Linux, reserve that, because what happens is that over time on Linux, as the kernel allocates and frees memory, it starts to fragment memory with the pages. And even though it has the memory, it doesn't have the contiguous huge pages that you need. In theory, you can also do 1 gigabyte pages, but I haven't gotten that to work yet. So yeah, so for 32 gigabytes, if you can do the 1 gig page, that's the 32 pages. And you don't care where in physical memory you are. It's just that the paging tables now being 64 megs are just a few K, and they all fit in the cache, and you never have to worry about it again. They all fit in the TLB for that matter. Yeah, if you're using the 1 gig pages, yeah, it's never gonna be out of the TLB. And even if we do context swaps and stuff elsewhere, it's never gonna be out of the TLB. It's awesome. So that's what you want to do for reserving physical memory is do the huge pages. Yeah, so I mentioned this already, collocate the data. I'd also compress the data. A lot of the stuff that you do, you can compress. Like, I've got a number that's between 1 and 10. Well, I don't need a byte. All I need is 4 bits. So use just the 4 bits. So what you're looking for here is trying to reduce the amount of memory that you use, but also think in terms of cache lines. The cache lines are 64 bytes on x86. Every time I go from one cache line to the next, that's a performance issue because it might not be there, it might conflict, it might toss something else out of memory. It might have conflict when there's two threads that are accessing the same cache line at the same time. They're conflicting now, have bounced the cache line between the two threads, even though they're not actually accessing the same variable within the cache line. So you want to sort of arrange your data structures on a per cache line basis, so you want to play with bit fields and stuff. Playing with bit fields is actually very, very cheap on x86. You've got 4 execution cores now on x86. So these cores aren't being used. And you're only getting maybe 2 instructions per clock instead of the full 4. And bit fields, all they really do is just increase the number of instructions you're executing, but not the number of clock cycles most of the time, or a lot of the time. It's a lot faster than you think. Also, instead of using 8-byte pointers for things, maybe having a base pointer and then an offset and index your data structures that way. Also, data structures have padding, get rid of the padding. So think about the cache lines and what you're doing and how big your data structures are.
Now, when you say get rid of padding, is that as simple as saying pack structs to GCC?
Yeah, but you don't want to do that. You want to do it manually and move things, rearrange your things until there's no padding. You can tell, I think, some compilers don't know about GCC, but you can tell it to say warn when there's padding, and it'll warn you.
GCC by default will add padding to a data structure.
Well, by the spec, it has
By the
to.
spec. But if you want a packed data structure, such as a packet, you add this.
But you don't want to do that.
attribute, packet.
Yeah, you don't want to take a packet and overlay a structure.
It occurs to me that it might be actually cheaper to add padding to the packet if you're developing a new protocol.
You never want to cast a packet. You never want to use packed. Is my theory. Packed is wrong. Packed is evil.
But the C spec does not say anything about how the packet is laid out. Sorry, a struct is laid out in memory. So
well, it says that they're in order.
Does it?
Yeah.
Yeah. So that A becomes before B, but there can be a padding between them. Yeah, I just do it in practice so that it's still virtual, that there's no packing going on, but yet lay it out so that I know that there's no padding going on either. But still, the code can't depend upon no padding. So if you're doing a mem compare between two structures, don't do that because there still might be padding somewhere else, like padding at the end of the structure or something. And then the mem compare won't work because the padding has some leftover bytes from something else. So another thing to Google is cache-efficient data structure. So again, academics at universities have gone through and said, well, how do we take a simple thing like a binary search tree and rearrange it to accommodate the fact that every node could be a cache miss as I descend the binary search tree. So instead, maybe I'll try to say, well, take a couple cache lines per node and put many compares. And so we'll do a linear search at every node. And so instead of n log n or log n search, it's now n log n or something like that. And so it's a different, it's more complex technically, but at the same time you're not getting your cache misses.
It's a B tree, right?
Yeah, yeah. But I just sort of search cache-efficient data structure and put something up here just to show you that at every node there's more going on per node in one cache line, so there's fewer cache misses. And there's lots of cache-efficient data structures that you can look at. And once you start looking at the cache-efficient data structures, the well-known structures, you can start thinking about your own data structures and say, well, okay, if I use this technique, I can, similar to this, I can get rid of some extra cache misses. Okay, so multi-socket CPUs add memory access, be aware of that. Yeah, the slab allocator stuff. You can control the prefetching. So one thing you can do is I got an incoming packet. Well, what I'll do is I'll pre-parse the packet. I'll grab a couple packets and pre-process them all and grab the TCP/IP socket information and then execute the prefetch instruction, which comes back immediately but tells the cache to go load the memory. And by the time I go and process the current packet, and then when I'm done, the memory for the next two packets will also be in memory. Now, be aware of this. It often leads to lower performance if you're not careful and don't benchmark stuff, but it can lead to higher performance if you're careful. Okay. Yeah, so Linux boot param, you can set how many, you should, for high performance applications, reserve your huge pages ahead of time. Otherwise, when you restart your application, the memory might not be contiguous. So the whole point of this was to get to this slide. So all those three sections I talk about packets, the network card, the CPU, and the RAM. And my idea is you grab your network cards and use PF-ring or NetMap to then take control of them, and now they're your network cards. They do everything you tell them to, and only what you tell them to. Same thing with the CPUs. Take them away from the kernel, take them away from the kernel scheduler, and you do your own scheduling, probably one thread per CPU. And you go grab, just go grab with huge pages the bulk of the RAM and do all your own allocation out of that. So what you have goes back to that switchboard picture that I showed, where you have the control system is the blue part, and then the control plane is the blue part, the data plane is your part. So you've still got SSH here, you might have a HTTP console type thing for controlling it, and then your Tor exit node or your DNS root server or your IDS running over here on the rest of the CPUs, outside the kernel. Yeah, the kernel knows they're all there, and still you interact with the kernel sometimes, especially over the control part, but the data is flowing through the system from the network card, through the CPUs to memory, and back out the other side without the kernel ever touching it. And that's pretty much the talk. The takeaways are scalability and performance are orthogonal. They're different things. You're making different choices. So when someone says, "Oh, you're just doing premature optimization," no, you're not. You're making scalability choices, not performance choices. These devices exist today. Everything I've presented exists. I've done it. Many other people have done it. And yeah, avoid the kernel. Kernels are evil. Just do all your own stuff.
There's a hardware-ish computer architecture research at UCSD where they recognize, okay, we've got this quad-core system. It doesn't scale 4x, and a lot of the cores are idle most of the time. So what they do is they run one program on core A, and they run a sort of shadow copy of the program on core B, but advanced, a few thousand cycles, and then and they run all the prefetch commands, and then the context switch switches the threads so that now the actual code is running over here, and the other one is prefetching ahead, and it improves performance a lot. It gets much closer to linear scalability.
Interesting.
Yeah, this is quite horrible, of course.
Of course.
Because that just
But then
tells
so
you-
is the state of multi-core programming.
Right.
Indeed,
So.
indeed.
The thing is, you can actually do multi-core efficiently. A lot of people are doing it now efficiently with a lot of free data structures and thinking a little bit more carefully about how they do stuff.
Right, but you have to program specifically with them in mind.
Yes, you do. You
And,
can't just
and it has to be fairly application specific.
yes, it does.
This the big problem is how do I do it generally,
Right.
right?
And so for me, I do networking stuff. So a lot of the models do become, you can generalize them. So what you do for an IDS or some things that also apply to a web server, it also applies to a Tor exit node, it also applies to a spamming system if you want to create a scalable system.
Well, sure,
to spam
because
people.
you've chosen a data flow abstraction,
Right.
and you can optimize that and then
Right.
fit all of these specific applications into it.
Right. So all this presentation was about that networking model, not about, there's all sorts of other stuff. Yeah, I don't care about this. I care about networking.
Well, one good idea for a project, if you haven't decided on one yet, this is, and considering that you only have 2 weeks, it's a bit late to
But in general,
start a new thing. But
no one's really come up with a really good, robust user mode TCP/IP stack that runs off of PF-ring or NetMap.
What's wrong with the 6-wind thingy?
It's commercial; you have to pay for it. It's closed source.
Okay.
Which means that researchers can't like grab and do a test project. I think you probably call the company and say, "Hey, I'm doing a test project at the university," and they'll probably fall over themselves to probably help you because it'd be great marketing. But in general, it's not something we can pull apart, tease apart, and like make changes to and discuss those changes. So a lot of people have taken like the Linux stack and make a user mode Linux, and now it's user mode TCP/IP stack, but still it's not. It's still you really want to say I've got a source of packets like NetMap or PF-ring. And then my own system here with no interaction with anyone else. I could run it just off of a PCAP file, a file of packets, just run it through, and it'll still work. On Windows. Just all C and CC code. No one's ever written something like that. That would be an awesome thing to have.
or just measuring the effects of the numbers and the effects of cache effects on your network performance. So measuring that path and saying how many pointers you dereference and how many cache misses you incur and how that affects your overall timing of the thread.
By the way, I do want to re-stress this, that these devices exist today on x86, it's your standard PC, is that I talk to people a lot and they're familiar with Apache, the performance level of Apache, and they sort of think of that as sort of the limit of how fast the server is, that no one can ever get faster than that. And so just knowing that, it's like learning to fly. You know, when the Wright brothers, did their airplane stuff, they had examples of birds and insects flying. So they knew it was possible. They didn't know how to get there, but they knew it was possible. So that's probably one of the biggest takeaways of this talk, was that people are doing 10 million connections. They are doing 10 gigabits per second, 10 million packets per second. Even though your existing going through the kernel doesn't quite support that, people are flying. And so that even if you don't know how to get there, knowing that's possible is the biggest thing to remember.